over the past several days, we began by introducing the conceptual ideas associated with derivatives, and then we spent a long time talking about how to manually calculate derivatives using various formulas and rules. What I would like to do today and tomorrow is to take a little bit of a step back and talk about how some of the concepts that we've already learned, how derivatives can be applied to some quintessential real-life situations. And the quintessential examples of derivative applications are motion problems and finance problems. Usually, two different kinds of students end up taking calculus. Students who are interested in physics, engineering, and students who are interested in business. So the motion problem is for the physics and engineering students to give you a little taste of what's going on there, and the finance applications are for the business students. Application to motion. So recall that velocity was the instantaneous rate of change, aka the derivative of an object's position. Now in this line here, what I've written is that the velocity is the derivative of position with respect to time. And when you hear me talk about a derivative with respect to something, what that is telling you, the reader, is that in this situation, the input of position, the variable that is the input or independent variable, is time. So if I say in English that velocity is the derivative of position with respect to time, what I'm saying is that position is a function of time, and velocity is the derivative of that function. So this with respect to is telling you what the input variable is of position. Now acceleration is just referring to the instantaneous rate of change, the derivative of velocity. And again, here I'm going to specify that this is with respect to time. When I say this, I'm assuming that the object's velocity is being represented as a function of time. Time is the input variable. And if I take the derivative of that function, that's going to give me the object's acceleration. Now specifically today, we're going to look at the situation of an object moving in what's called free fall. Now free fall in physics has a very specific meaning. If an object is in free fall, that means that the object is moving under the influence of gravitational force only. So what does this mean in practice? This means that you have some object which is flying through the air, which is being dropped, which is being launched, and that object is being considered to have no air resistance. So either the object is moving in a vacuum, or the object is sufficiently aerodynamic that air resistance is so small that it doesn't really affect the situation dramatically. We're also assuming that the object is not in any way moving under its own power. So it's not like an airplane or a drone or a helicopter, which has some kind of motor or propeller that is influencing the object's movement as it is traveling through the air. When we say free fall, that means that gravity is the only force that's acting on this object and causing it to move down toward the Earth. Now, as it turns out, that when you assume that you have an object which is in free fall, there's an extremely simple quadratic equation that can be used to find the object's vertical position, its height above the ground, at any given time. So suppose that you have an object and you're measuring its vertical position after t seconds. Continuing along in the metric theme, we are measuring the position of the object using meters. Now remember, whenever we talk about position, we have to establish clearly what's our starting position and what's our forward direction, the direction in which position will be considered a positive number. And when we're dealing with free fall equations, the convention from physics is that the starting position is ground level. The starting position is on the ground. That would be a position of 0. We're also going to assume that the forward direction is up. So the object's position will be positive if it is above ground level. Final bit of fine print. The following formula really is only valid if the object is moving on Earth, somewhere close to sea level. We're still just setting this up. So, having assumed all of that, let's suppose that when the object first starts moving, its initial height is h0. And the object's initial vertical velocity, how fast it's moving up, down, is given by some quantity v sub 0, v0. In that case, what function would give the object's vertical position at any given time? The object's vertical position would be given by negative 4.9 t squared plus the initial vertical velocity times t plus the initial height h0. This formula will work no matter what object you're considering, whether it was dropped from the top of a building or launched from a catapult, whether this is a bullet or a shot put. This will work basically for any object as long as it meets the conditions that are set up in this paragraph here. This is a broadly applicable equation that comes up all the time in physics. Now, one final piece of fine print that I want to draw your attention to is that in this formula, v0, the coefficient on t, is specifically the object's initial vertical velocity. How fast it was traveling, either up or down, when the object was first launched. Now, the object's vertical velocity, generally speaking, is not the same as the object's overall velocity or speed. If, for example, the object is launched at an angle, then its overall speed is taking into account the fact that the object is moving a little bit up-down, but also a little bit horizontally. The vertical velocity would only be the portion of the object's speed that describes how fast the object is traveling upward or downward. So let's use that equation in the following exercise. We have an object launched into the air with an initial vertical velocity of 20 meters per second and an initial position of positive 5 meters. So with the conventions of the previous formula, this object will have been launched from a position that is 5 meters above the ground. So let's find a function f of t which gives the object's vertical position after t seconds. All I really need to do is I need to fill in the blanks of that free fall equation given before. The number v0 stood for the object's vertical velocity at the initial time, and that's given to me to be 20 meters per second. The h0 was defined as the object's initial position, and that's given to me as 5 meters. So if I just fill in the blanks of that general equation, I get the answer that the object's position at any given time is equal to negative 4.9 t squared plus 20t plus 5. Now that we have the object's position function, let's find a function v of t, which gives the object's velocity not just at the initial time, not just at time t equals 0, but at any later time. Remember that the velocity is just the derivative of position. So all I need to do is use the derivative rules to find the derivative of the function f of t from part A. So the derivative of negative 4.9 t squared, the 2 will come down, the exponent will change from 2 to 1, and I'm left with negative 4.9 times 2t. The derivative of 20t of number times variable is just the constant number, and the derivative of the constant 5 is just 0. So if I simplify this, I get negative 4.9 times 2, which is negative 9.8, t plus 20. 20 is the vertical velocity when no time has passed, when t is 0. This is going to give us the velocity at any later time. Question. Specifically when the object hits the ground, what is the object's vertical velocity? So to answer this question, let's see if we can figure out specifically at what time the object hits the ground. Now, when we set up the free fall equation, we had the convention that ground level meant that position was equal to 0. So let's find the time at which the position of the object was equal to 0. Now we have a quadratic expression on the left, we have 0 on the right, which means that this is the perfect opportunity to use quadratic formula. You remember quadratic formula, y'all? Which says that the time is equal to, you ready? Negative b plus minus square root b squared minus 4ac all over 2a, where b is 20. Now I've gone ahead and estimated these two solutions on the side. One of these solutions is negative, and we won't be considering that because that would be technically before the object was even launched. But let's go ahead and use the positive solution, t equals 4.3. The object hits the ground, roughly speaking, 4.3 seconds after the initial launch. So if that's the time when the object hits the ground, we can now take this time and plug it into the velocity function to get the object's velocity when it hits the ground. So that would be negative 9.8 times 4.3 plus 20, and according to my side work, that is negative 22.14 meters per second. Now let's check just for a minute to see if this object makes sense. We have an object which is in free fall, and if I look at the object's vertical position, its height over time, the object starts at a height of 5, is launched upward at an initial velocity of 20 meters per second, so it's going to be carried upward by that motion for a while. But gravity is constantly acting on this object to pull it back down. And so after a certain period of time, the object is going to begin to have a decreasing height until eventually it hits the ground at some later time, which we found to be 4.3 seconds. So it completely makes sense that the object would have a negative velocity at the time when the object hits the ground, because a negative velocity means that the position is decreasing, which means that the object is moving downward. So by taking the derivative of position, we found a function which gave us the object's vertical velocity. Using that formula, we can answer all kinds of questions, with one example being, when the object hits the ground, what is the object's velocity at that moment? Let's see if we can find a function a of t, which gives the object's vertical acceleration after t seconds. To find acceleration, all that we need to do is find the derivative of the velocity function. The velocity function was this linear function here, and if I find its derivative, the negative 9.8 will survive and the plus 20 will vanish. Now the acceleration is given in units of meters per second squared. And in the case of an object in free fall, the acceleration is constant. The acceleration at any time is equal to negative 9.8 meters per second squared. The number negative 9.8 meters per second squared is called the acceleration due to gravity. An object is in free fall, so that object is being acted on by gravity alone, and so gravity is the only thing that is causing that object's velocity to change in any way. Negative 9.8 is called acceleration due to gravity. Now this number is the acceleration due to gravity on the planet Earth near sea level. But on other planets or at other elevations that are very far from sea level, this number will be different. For example, at higher elevations, this number will not be quite so large in magnitude, maybe 9.7, 9.6 instead. Now, one technicality that I want to draw your attention to when it comes to official physics language is the difference between speed and velocity. When we are talking to each other colloquially, the words speed and velocity usually mean roughly the same thing, how fast an object is moving. But these two quantities are technically different. Velocity is almost the same as speed, except velocity is allowed to be negative and speed is not. So technically speaking, speed is the absolute value of velocity. For example, if I were going to go back to the free fall example in number 1, we had a velocity function that was given by negative 9.8 t plus 0. That's the velocity. If I wanted the speed, I could just take the absolute value of that. That way it's no longer able to be negative. The absolute value forces it to be a positive number. And if in particular I was going to check out the speed at 4.3 seconds when the object hit the ground, then the speed of the object at that time would not be this number negative 22.14. Speed would be the absolute value of that, would be simply positive 22.14. And this is going to be really important in calculus 2. There are going to be some formulas which are described in terms of velocity, and then there are going to be some formulas which contain speed. It involves this absolute value here.